So I'm about to introduce our next month's speaker, and I have a few things to say before we get into that. There's all sorts of different types of astronomy, and I think what we're going to be talking about is galactic astronomy, where you want to see how does a galaxy form, how does it behave, how do galaxies interact, how do they age, what's the evolution of galaxies. And to study that kind of astronomy, you need to know what are the dynamics within a galaxy, or how do the stars move, what's the chemistry of stars in different areas of the galaxy, and so forth. And to get information about those things, you do what are called surveys. So there's a survey called Apogee, and this is a survey which constitutes high-resolution, near-infrared spectroscopic studies of several 100,000 stars in the Milky Way galaxy. And spectra are observed with a custom-built multi-object spectrograph. So imagine, so here I found this picture online. It's related to this Apogee study, which shows some part of our galaxy, or maybe the Small Magellanic Cloud or something like that, something nearby. Is this the Small Magellanic Cloud? And is this the field of view of the instrument? Yeah, and so then you get all these stars, and the neat thing about this detector is it samples the spectra of all these stars simultaneously. And if you got a spectra to gather from 100,000 stars, you don't want to do them one at a time. It would take too long. Now, what's really interesting is that this first spectrograph, the Apogee spectrograph, was constructed and assembled primarily at the University of Virginia. And it was built for this Sloan Digital Sky Survey, Apogee survey, which covers the northern hemisphere. And then a second Apogee spectrograph operates in the southern hemisphere at the 2.5-meter telescope at Las Campanas Observatory in Chile. And that covers the southern skies. And our speaker tonight, Andrés Almeida, back there, will tell us more about how these instruments have been used and what they have taught us about stellar populations and the dynamics of our Milky Way galaxy and in the Small Magellanic Cloud. You will try to make sense of it. Andrés is familiar to some of us because he lives right down here in the Vysotsky cottage, and he is the guardian of the Leander McCormick Observatory. So if you show up at night unannounced, he will come out and find out what is going on. Andrés is also currently working on his PhD at UVA. Thank you.
You have you shared it with us, or do you have your own?
Yeah, I don't know. It should be open on there. That in the it's a Google.
I see this right
Like
here.
that.
I see. Perfect. Great. Is this also right here?
Yeah.
Perfect. Would you like me to run the slides for you, or I'm happy to do it for you? Slide.
Okay.
All right. Can the okay, that's not sharing, I don't believe. It's supposed to be done. Excuse me. Think. Can the viewers online see the can the viewers online see the presentation?
Yes.
I think they can. We can probably go ahead.
Did you get a thumbs up?
Not yet, but I think that they should be able to, because both of them are showing.
Yes.
There's a lot of things on the screen. Sorry, this is usually shared to a separate. All right. Is that all right for you, or would you like?
Yeah, it's okay. Okay, thank you for inviting me.
The microphone.
Oh, the mic. Oh, thanks for reminding me. Sorry. How much did you order?
All the video. Okay, as I was saying, thank you for inviting me for giving this talk. Okay, Kevin told me that it had to be a 45-minute talk, long talk, and I was like, geez, I have never done a talk like this long, so I will try to make sense of everything. I will be speaking a lot of concepts and stuff which are related somehow, okay, but Also, I am from Chile. Okay, I have an accent. I tend to speak very fast. Even for a Chilean, I speak faster than a regular Chilean. So if I begin to speed up too much and you are not understanding my speech, please let me know. I will get mad, but I will. Well, the title of my talk is the SDSS-IV APOGEE-2S Journey and Beyond, from plates and fiber to robots. Maybe the the title is a bit misleading, but all the making of this Apogee survey was a total journey, and it was something and beyond. We will see what happened after that. Okay, next one. So, okay, I will be speaking a little bit about what is the SDSS, the Sloan Digital Sky Survey, how we did make Apogee-2S, some of my science results using the data from Apogee, and what about the robot and SDSS-V, the next phase? You can see me here coursing the skies because we had a week of bad weather. We couldn't observe for a week. So we took the decision to sacrifice an observer and it cleared.
Sacrifice an old server?
Yeah, to the god of the Pachamama. So
Couldn't find Virgin, right?
yeah, no, it was impossible there, but the youngest one was perfect for the second. Okay. An introduction. Okay. SDSS-V, Sloan Digital Sky Survey, it began the operation in the year 2000 with the first phase, SDSS-I. Right now we're running the SDSS-V, okay? And by the end of the SDSS-IV, it created one of the most detailed maps, three-dimensional maps of the universe ever made, with multicolor images of the sky and a spectra for more than 3 million astronomical objects, okay? Next one. The survey. Each phase was component by several surveys. SDSS-I is kind of called the pre-legacy, the starting point of the SDSS. SDSS-II was composed by three of them, the Sloan Legacy Survey, SEGE, and Supernova Survey. Both SEGE-II, Mars, and Apogee was for SDSS-III, SDSS-IV, Manga, EBOS, and Apogee-II. And SDSS-V currently observing with the Milky Way mapper, black hole mapper, and the local volume mapper. And sorry.
Oh, sorry.
You can see one of the images taken by the Whirlpool galaxy. Next one. This was carried out in the Apache Point Observatory at the beginning. It's still working there, SDSS-V. This observatory is in New Mexico, very close to Alamogordo, okay? You can see here the white sands, and there is a missile range there and Air Force base. You sometimes can see the planes and the fighters doing some stuff. And the telescope we used was this one. That's the 2.5 meters SDSS telescope. In this observatory, there is another bigger telescope, the 3.5 ARC telescope. And beside this, there is the Solar Observatory in Sanford. All a big astronomical facilities. Next one, please. Okay, so this telescope was exclusively was made just for the SDSS. It's a survey telescope. Okay, has an azimuthal mount, and this telescope, a difference with many others, doesn't have a dome. You just have an enclosure. You have to move by the end of the day, and the telescope is totally free of the turbulences and seeing inside the dome, which is very good. The downside of that is sometimes it begins to rain, and you have to cover your telescope very fast because you don't want the equipment to be compromised. It comes also with these pedals, which can be closed to take flat images on the fly. So it's a very efficient piece of machinery they made there. And it was, as the legends say, 2 talks away for not being built. So this, you can see back in the year, the first part of the the 2.5 meters telescope being made. Next one. Okay, the first phase of the SDSS. It was done by this beautiful camera, the SDSS imaging camera, which has four filters, and it took simultaneous images of the strip of the sky. Okay, it obtained also. They have another small spectra with this camera, and obtained a spectra as well of galaxies, quasars, and many stars in the Milky Way. And they were found the first streams in the Milky Way, which help us now understand the evolution and how the Milky Way came to be together. Okay. Right now, this camera is in the Smithsonian Museum in DC, and yeah, it's a piece now of history. Next one, please.
Excuse me.
So is that camera like a gigantic sensor?
Yeah. All
Because
this,
that looks big. It looks like,
you can see the detectors, yeah.
it looks like it's several feet across.
And the way, sorry.
Odds there, can you describe how it functions? I mean,
I'm not that familiar with this camera. I just know that the filter didn't change. They were just drifting over the sky. So one strip of the image was in one filter, another one in another, and they repeat. A small drift, another piece of the sky. Yeah, the SDSS-II was an extension of the SDSS-I because at the beginning they didn't believe that it will be successful. They got to get more money because we need more data. The data is amazing. And this worked from 2005 and 2008. And they made this beautiful with this data. One of the first map of the big scale of the universe. Still not reached that high, but still was one of the biggest slices of the known universe. Some galaxies, they took so many images. Next one, please. One of the surveys they had was the supernova survey, which was repeating taking images from a section of the sky, repeating over time, trying to detect all the supernovas they detected there. There was a very successful small sky survey for the time.
Is that supernova in our galaxy?
Yeah.
In the Milky Way?
Yeah, the Milky Way.
Wow.
Yeah. No, the Sloan Digital for Galactic Understanding and Exploration, SEGE, it was the first point they tried to prove the structure and the history of the Milky Way with the spectra of almost 250,000 of stars. This one. For the SDSS-III, new technology had to be built. And they also began to look now to more quasars and black holes in the universe with the Baryon Oscillation Spectroscopic Survey, BOSS. SEGE-2 was an extension of the first attempt with SEGE-1, and APO, the APO Galactic Evolution Experiment, Apogee, the first phase of the survey, began to delve into big sample of RGB, red giant star population in the Milky Way. Marvel was taking care of detecting planets, variation in velocity in the star, so for candidates for exoplanets. That's one, please. Yeah.
Question about, I was just looking at the plots in the right there. So we're measuring metallicity of the stars as a function of radius from the galactic center. Is that what I'm saying? So
Yeah.
lower metallicity further out.
Mm-hmm.
Okay.
Okay. Okay, one of the new technologies was the BOSS spectrograph, who could observe 1,000 objects at the same time. It was an optical spectrograph with a resolution of 2,000, if I'm not mistaken. It was one of the first big ones they had. And I will explain a little bit what is all fibers and plates and how they collect the data. Next one, please. As Boris adelante, preview in the teaser, yeah, the Apogee spectra were built in the astronomy department of the UVA.
Just a quick question, on the one before this one, just for a second. Are each of those fibers, do they represent that it's pointing to one object in the sky?
Yeah.
Every one of those?
Do you want to
Yeah.
talk about the plate?
There's a. I will show about the later, the bit later, okay? But yeah.
Okay.
Each fiber will go to one node in the sky. Yeah. The Apogee spectra is a big spectra, as Boris say, it's a multi-object spectrum. It can take the spectra of 300 stars at the same time. So in a night, we can observe 5 or 7 fields. You can do the math. We have several thousands of spectra per week, you know. This is the way it was departing from the UEA and arrived to APO into the clean room they have there, which is not that clean. It has some flaws in the design, and the last time I went there was in maybe 3 years ago. Where I went with John Wilson, which is one of the scientists who designed this, and we have to remove thousands of moths there. Yes, moth from the clean room was a total mess. We have to open the instruments, so we had to clean everything. We spent like a week removing moths. It was super gross. But well,
So
now it's clear.
That was.
We were
designed-
super sure it's
It
clear.
was designed and built here at UVA?
Yes,
Wow.
yeah. The spectrum was designed here. They have to build a lot of new technologies for that spectrum. They designed a holographic grating for this, for the light to be decomposed.
Yeah.
It's a really nice piece of engineering. Okay, next one, please. Okay, so now we will talk about more in detail about the Apogee-2S. Okay, next one, please. Okay, the PI of the is still here. Steve Majewski, yeah, Steve Majewski. This was done by a former PhD student from UEA. He's a student 10 years ago, maybe, or maybe more. The new thing for the SDSS-IV is can view the whole Milky Way. Why is that? Because we started looking from the south, in particular from the Campanos Observatory. Okay. That's one. Here you can see all the fields that Apogee actually took data in all this year of operation. And you can see the sun here, we are here, and we are looking in all those directions and covering a big chunk of the Milky Way. The spectra, high resolution spectra can give us how are composed the stars, the velocities, etc. And one key element of this is we are observing in infrared, and there is a reason we need to go through the dust of the Milky Way. The Milky Way has a lot of stars, has a lot of dust as well, which occurs. We cannot see the stars in the visible, but in the infrared, we can actually see the stars. So we can go and see the bulge of the Milky Way, for example.
How far into the infrared?
Hmm?
How far into the infrared?
Oh, it's near infrared.
Hmm?
Near infrared.
Here.
Near infrared. No, not that far, but enough to traverse the dust. Yeah. Next one, please. Okay, and the telescope we use for this is the DuPont telescope. This telescope is a bit old. It was built in 1976. This is the year actually it started operation, but it's a really fine telescope. Okay, it has a mirror of 2.5 meters and has an equatorial mount. And you can see here inside the dome is huge, which did some issues at the time of observing, but I will explain that later. Okay, at the beginning, before the instrument and everything came there, we needed to prepare everything there. Okay, and you can see a very young version of me there. Even yeah, Jesus Christ.
Was the telescope not in use?
Was in use, but we needed to prepare infrastructure for all. Yeah, improve the telescope, but also we have to make infrastructure build a machine called the mapper. I will explain that later. This is what will be the skeleton, how we will load all the new equipment into the telescope. All of this was made in the Universidad de La Serena, and we transport everything to the observatory. That's one piece. So, as you said, a lot of adjustment to the telescope itself needed to be done. It's an old telescope, but it's still very precise, but has its flaws. So we have to recoat it, the mirror, clean the mirror, and we did several engineering runs testing the accuracy of the pointing of the telescope. When we were ready, and the spectrograph was in his place, the spectrograph who looked like a big smoker. It's true, huh? It looked like a big smoker. It arrived to the telescope. And here now is in his new house, the second spectrograph. They built 2 spectrographs. This is a way more clean room than the one and mostly because the Atacama Desert is very arid for real. I mean, there is nothing there, living there, nothing, or almost nothing. So there is no more. Okay. Okay. I've been talking about a bit about the spectra. Are you familiar with what the spectra is? Okay.
Okay.
It's just to be very blunt, to decompose the light and analyze that. Just that. That will give us the component, how a star is composed, some doublers. Some information can be derived from the spectra, like the velocities of the star, etc. The gravity, the temperature of the star, stuff like that. This is how Apogee spectra look like. This is a temperature sequence made with Apogee-1 for this kind of star. And you can see the observing lights before the processing by the pipeline. Okay. Okay. And what you were showing was this image with John Wilson. It was the first light of the Apogee-2S. It was the first time that Apogee looked into the sky and took a high resolution spectra. It was a moment of joy because we spent like 2 months trying to calibrate everything. The commissioning time for Apogee was insane. I remember that I had to work the 2 shifts, night and day. I couldn't really sleep because I had to fix the stuff that were running the night, and unless it was crazy. But good time. I mean, I learned not to sleep, so that's a good skill. Okay. Okay, so I've been talking a little bit about plates, etc. But this is a plate for Apogee-2S. Okay. We have over 1,000 plates in the room there, and each point you see here is a star in the sky. So all the plate is a region in the sky. We have 300 holes, 300 stars, and you can see also here there is some star with a number. That is for the guidance stars. And these big holes are for extra camera for the acquisition of the field. Okay. Later you can see the thing by yourself. Okay.
Do you have to feed those fiber lines to that each plate by hand when you're going to use it?
You will see that.
Wow.
No, it was a journey. I told you. This one, please. So this is how fortune of the sky look like, and yeah, each dot will be an Apogee target, and yeah, luckily it's not really going to the star we decide to go. Next one. Okay, so we have a plate, and where the plate goes, it goes into this small stuff called, not small, it's kind of big, called the cartridge, a card. Okay, a card is populated by 300 fibers, fine fibers, which end in a little hole. You will see later. This machine we built in the university helped us to manage the card. The card was like 200 pounds, I think. I could lift it, but most of the other people couldn't. But Yeah. But this machine helps us to lift the card, turn over the card, etc., etc. Okay, next one. So you can see here the process of installation of a plate by one of the observers. And this plate needed to be bent. Why is that? Bent.
Local planes.
Exactly. We have to match the focal plane of the telescope. Okay, we have to be very precise with this. We have a specific way to put torque into the wrench, into the screws. Okay, next one, please. So yeah, this is the plate installed, already bent in the card, ready to next one to be plugged. As you say, we have to plug every single fiber by hand, and you have to be very careful because the fiber, as you can see later, has the diameter of a human hair. It's very thin, you know.
How long did it take for you to do one plate?
For me, when I was high in caffeine,
Yes.
I would say 50 minutes to have everything ready for a card. Plug, bend, everything ready to go to the telescope. 50 minutes, yeah. But in average, I would say it's 40 minutes, 45 minutes. Other people were more slow, maybe 1 hour for the beginners. But people were getting fast because we're doing this every day, almost every day.
So then it took you like an hour and you were really fast. You would probably not do that more than, if you would do that and then use that plate for a day or 2 days?
Not really,
You would do
because
it
we had,
on-
can go back one. We have 5 of these cards. So we could prepare the card beforehand, the night. We can 5 card prepared. And in the night, you could observe maybe as both 9 plates. So you remove a card from the telescope, you unplug that one, and plug a new one. It was a really big operation. But yeah. So yeah.
There's a lot of red, blue.
Oh yeah.
So how do you,
Thank you.
yeah, how do
Thank
you,
Yeah. It's important. The fibers were color coded. Okay, in blue, black, and red. The blue ones was for the more bright stars, black, medium, luminous star, and the red one was the faintest star. The idea is that the algorithm will never put a bright star too close to a faint star because you will have contamination. Okay. And
Yeah, they're color coded there in the circles, you can see.
yeah,
Down
Oh,
close to the camera, 2 blue ones that are red and black
gotcha,
on the left there.
you see.
okay.
And this other, it has a small hole. I don't know if you can actually see that. Because the light fiber had an alignment pin because we needed to know the position of the star in the sky. For the other fibers, doesn't really matter. Just get the light, but we need the position for the other one. Yes.
So each one of the one ends that we're looking at goes into, I guess, whatever it is.
Yeah.
And that is going to be a position where a galaxy is,
Star.
or an object, correct?
Yeah.
Where does the other end of that fiber optic?
The other end
go to?
go to the spectra.
Go to the spectrum.
All this fiber you see here, and in a small chunk, another small chunk, and a connector was called the GAN connector, who was like 20 meters long at least, to feed the spectra, which was in the basement of the telescope.
Sorry. How can you be so exact as to know where the position of something is going to be on a plate?
Oh, can go back, please. One more. Back. Okay. Yeah. This machine also had a connector who was fit with a laser which was moving. So we took pictures of the blade after we plugged, okay, and we know fiber 1 is there, fiber 2 is there, etc. So you have a map of what you're seeing. It's very important to be very accurate because if that is messed up, nothing will go. Okay. So here is the plate ready to go to the telescope. Okay, next one. And this is the GAN connector. This is feeding the acquisition cameras. And this is a fiducial fiber for the flexure of the guide camera to correct the flexure when the telescope is moving, and it will be a separation, and everything will be a full calculated and offset to compensate the flexure of the guide camera.
So the GAN connector has the 300 fibers in it
Yeah,
that are feeding light from the 300 different stars. And that goes in the basement, which is where the actual, into that clean room.
in the real clean room.
Effectively.
Exactly. Yeah. Yeah. So they say that all this chunk cost like $250,000. So it was very sturdy, but it could be broken because we didn't broke that stuff. If we had an accident that we done, broken, the project was done. No more money for that. Yeah. So we have to be very, very careful. Okay. It's important to note that, yeah, the telescope wasn't that precise, and we came with an idea of installing acquisition cameras, extra acquisition camera for into the blade to point. Once we had these stars, we could move the telescope and put the 14 guide stars into the fibers. Okay, this has to be very precise because, as you see, it's very thin. It's human hair. You have to put the light not in one human hair. You have to put the light in 300 human hairs. So the guiding has to be super precise. Okay. Okay. And yeah, these people, and this is very important because we have to come with a model of operation, because some people we need to prepare the plate, other people we need to operate the telescope, the instrument at the same time. So we came with this roll chaining per day, and we have two models in summer and winter, with early, late, some flyer and observer, and we were 4 working at the same time. So the idea is to have the people always refreshing, cross-training with everything, with any of the labor, and refresh enough to not make mistakes, okay? But of course, pandemic hit, and we had to modify part of the operations, part remote, and some people in the mountain because we have a cap of 2 people in the room, and some people were behind remotely observing, and we have to have people, extra people in the telescope actually managing the stuff.
What was the total time from the idea to do this until you had the thing built and ready to use? How long did that take?
I don't.
When you, from the design of that device until it was actually ready to use, how many years did that take?
The spectrograph?
The spectrograph?
Yeah,
Several years.
several?
Yeah.
Yeah, okay.
I mean, yeah, the design for the first was several years. Yeah,
Okay.
for sure. The second one, oh yeah, the second one has to have an extra device to dampen the earthquake. Chile is a country, we have so many earthquakes. New Mexico doesn't have any, so they don't care about that. But yeah, and there is a device in the spectrograph to damp the energy of the earthquake. Yeah. Oh yeah,
Who's that guy?
yeah, I don't know. It's some guy who was there.
Oh.
Oh,
You better request access?
yeah.
Won't be access to my tax record, that's all I'm asking.
Yeah.
Right.
Yeah, this is a time lapse of how the telescope was working in the night. We observed mostly in bright time. So when the dome opens next time, it will be a moon, and you will be able to see. Yeah, data.
I like the way the screen is sparkling.
Yeah.
Yeah, that's the boombox.
Oh, move like that.
Yeah. Yeah, you have to observe. Yeah, that's the way the people change the cartridge every time.
Change the cat,
Yeah,
of which you had 5.
exactly. Okay, next one. Okay, the legacy of Apogee. Okay, almost 3/4 million of stars, three-quarters of a million of stars in the Milky Way, and just over 250,000 were taken in the south. In over 4 years of operation, all data from SDSS is public. That is very important to remark. After a year, every observation from the SS will go public, and you can use the data, you can look at the data, you can make sense of the data. More than 10,000 citations has the SDSS paper right now. So, no citation, more than 10,000 articles using SDSS data, and the citation for those papers are over 100,000 at this point. And just because of this is very important.
As these different stages have occurred, as the density of the spectrum evolution increased. As you've gone through these different stages of the survey, does the spectral resolution increased?
It will depend in the objects. If the objects are you observe the object with SEG and then Apogee, yeah, it will be an increase. Yeah. Okay. So I will talk a little bit about the science result I have. I have the luck of observe the Magellan clouds in the south. And for who are familiar with the Magellanic Cloud, the most massive dwarf galaxies which are orbiting the Milky Way. It only can be seen from the south. Okay, has a number of gaseous stars and substructures around the SMC, the LMC and the SMC. And next one. This is the way you can see with your naked eye. Actually, this is in La Silla. It's just in front of the Las Campanas. This is the large Magellan Cloud. This is the small one, and this is the arm of the Milky Way. You can see that from several places in Chile, and especially in the observatories, when you have the sky just there, you know, it's really. So the good thing of the Magellanic Cloud are quite close. It's galaxies which are interacting. Okay, and we can identify some superstructures in these galaxies, okay, that come from this tidal interaction. Some of them, we tried to make an explanation of how come that happened. Okay, this one. It is known that in the Small Magellanic Cloud, the eastern side, which is facing the LMC, has a deeper line of sight, and is kind of more bigger in this side than the other, or more profound in this side than in the western side. Okay, and using red clamp star, which are universal candles, they found a bimodal distribution of two populations of red clamp star. One in the systemic, let's say, distance of the SMC, and other subpopulation was in the front. Okay.
So what's the left column? So this is the bimodal distribution.
Yeah.
Where is this one from? The left column.
The left column is this magnitude from the.
Okay, so that's a normal, and the
Yeah.
right one is the eastern side only.
Yeah.
Okay.
So the goal of this paper was understand the origin of the bimodality using stellar kinematics and chemistry from Apogee, and comparing the properties of the bimodality fields with those of the other region of the SMC. So we took next one. Yeah. So yeah, this is the data we use. Sorry, I was ahead on myself. We use a combination of Gaia, proper motions, and Apogee to South data. And this is the field over the SMC we observe with Apogee, and this is the field we observe over the LMC. This one. So we need to know how we will divide the SMC, the Magellanic Cloud, the Small Magellanic Cloud. And we define it, this is what will be the eastern field, the center, and the periphery of the SMC. And we compare the properties of this field. This one, please. And we found this. Sadly, RGB stars, red giant branch stars are not really good for determining distances. But we use at that distance proper motion as a proxy at distance in the skies. And we can see that the eastern side has a prominent peak, which is not seen very much or at all in the center field and in the west field. This one. What happened with the velocity? Yes, the velocity show also that the eastern side is moving different than the center, sorry, not back, center on the west. So what we did, we divided the eastern fields in a near subpopulation and a far subpopulation, and we did the same. This one. And we found that the east near subpopulation are the one which is actually moving different from the rest of the SMC. Okay, that's one. But what about, yeah.
I have a question. Presumably those, the Magellanic clouds are orbiting the Milky Way.
Yeah.
So they have orbital motion associated with that. I don't, a couple of questions. One is the magnitude of that intergalactic orbital motion, how would they compare to these numbers? And two, is there a, leading edge, trailing edge? Or maybe I thought you said RAM at one point, but
It can be, but actually the Magellanic Cloud is the fifth infall into the Milky Way. It hasn't been before orbiting the Milky Way. That is it was discovered a few years ago. And second, yeah, that velocity is accounted here in the model I applied for taking these velocities.
Well, I was just thinking, what is just the purely orbit, if you took the mean motion of all the stars in the cloud, what would that be? The mean orbital motion around
will look like this in this frame of reference.
So this is corrected for both revolution and rotation.
Yeah, it's corrected by bulk motion of the SMC and rotation as well.
Yeah, I was just wondering what the kind of the absolute, not in the co-moving reference frame.
Okay,
but
yeah.
Absolute reference.
You mean the traverse velocity you will see?
Yeah.
Yeah, the traverse velocity is around 400 kilometers per second.
So
Yeah.
this is like 10% of that. Or
Yeah.
5%, whatever.
But then again, that is corrected by.
That might be relevant if the cloud, I'm just spitballing here, if the cloud is like ramming into the intergalactic medium.
Yeah, that can be an explanation, but we are looking into that actually. Okay. So what happened with the chemistry of the stars? And we can see that the center and the east are slightly more metal rich than the other ones, and actually, which is the near subpopulation, which is the one which is more similar to the center actually. The far population is more similar to the halo or the periphery of the SMC, which was to be expected.
But is noticing record, is that reference to our sun's metal content?
Yeah, but these stars are very old. Usually, the SMC has to say his 1/4 solar metallicity, But yeah, this is very old and can be different.
So you say metal richly is strictly speaking.
Yeah,
iron, just iron, or is it all
iron.
metals?
We have seen others, and it's the same behavior.
Okay.
Okay, so the center and the east near population share the same chemical signature. So that next one. The interpretation is the LMC and the SMC has been interacting before several times, and the last time was kind of 200 mega years ago. So we are saying that maybe this is material from the center of the SMC which were put out from by the LMC in the last interaction. Another explanation, which is brand new, and also I work on that, and we are seeing that really happening. It can be another galaxy, actually. We are seeing there. We are seeing the Magellanic Cloud, the Small Magellanic Cloud, and in front of another dwarf galaxy. And yeah, the project I've been working, that one, is with some binary stars, also using Apogee data. This one. Why we are studying stellar multiplicity or binaries in just because of this, they form almost all the form most of the stellar source of gravitational wave, which is a hot topic now. Okay, we help us understand the different stages of stellar evolution, and have to find fundamental properties like masses and distance. Okay, that one. So this is a trick of how the many outcomes of the binary evolution you can have, and this is simplified. I think this even wider. This one. So our inspiration of the work is an old work from it's a previous work from 2018, and they use a combination of metallicity, temperature, and gravity along the radial velocity. The next one. To find variation in the maximum variation of the radial velocity of the stars. The good thing that Apogee usually have several stars more than once, 3 times. So you have a bit of time domain there, so you can see not enough to make orbits from the binaries, but you can see this difference in the delta RV max, and it's correlated with the gravity as well. And they found that the low metallicity stars had a bigger fraction of multiplicity than the metal-rich stars. This was applied, we applied this method for seeing what we can say about the Magellanic clouds. Next one, please.
Is that
So, yeah.
because the gas clouds in the early universe were more abundant, and you are more likely to have more stars forming in the same region than later stars, which have less gas to form from because it's already formed mostly into stars?
And more density of stuff as well. So it gets this loop. There's several possible explanations, but one of them is that, yeah.
Okay. I just want to clarify a few things. When you talk about metallicity in stars, you're talking about age. And the low metallicity stars tend to be the very oldest.
Which-
You mentioned something about halo stars. The halo stars around our galaxy were the oldest.
Yeah.
And so here you're correlating metallicity, in effect, age, with how many of those stars are involved in binary or multiple star systems.
Mhm.
And you're finding that the oldest populations are more likely.
They found this. I did.
Oh, they found that the oldest
Yeah.
populations are more likely to be
Mhm.
binary.
The fraction is bigger. You see?
I think so.
So does this imply that as we go to younger generations of stars, that are you saying that the fraction of singles is rising in essence?
I will say.
They don't have the social skills.
But,
It's the internet.
because if I'm trying to go along with what I'm saying, is that the metal poor stars tend to have a higher fraction of multiples, right? Is that what you're saying? No.
We can talk later more of that. Okay. Okay. Data set is a bit different from Badenes, since we have for the SMC and the LMC more visits, more difference, more a way to explore more these radial velocities. Okay. And we can compare that with the same with a control sample with the same gravity range of the Milky Way. Okay, next one. So this is what we are seeing in the spectra. These are the difference in the Doppler effect of the RV max. Okay, with 5 epochs. And the preliminary results. This is important to know that this is with a very low signal to noise. We have to be careful with this result because the stars of the Magellanic Cloud are farther away than the Milky Way. So we need a higher, sometimes, signal to noise signal per se. But if you continue, we are finding constantly, next one, and the next one, that the Small Magellanic Cloud has a bigger fraction of binaries than the Large Magellanic Cloud. And at the same time, those two galaxies have a larger, or apparently have a larger multiplicity fraction of close binaries as the Milky Way.
Is that because the Milky Way, is there also a correlation? And I know the
I would say
clouds
the
are less metal rich.
metal rich and less dense as well. The difference of, yeah.
There's less binaries because they're less dense and less metal.
And more. Usually, as far as I understand, when a star is forming, it has a lot of nodes at the same time. Most of those nodes, when the environment is sometimes not very, it's too dense, it gets ripped for another in the same region of the star formation. One of the explanations maybe is that the Small Magellanic Cloud has less metals, less gas, but it's less dense as well than the LMC or the Milky Way. So maybe they tend in that way to survive more these binaries, and we are seeing more. There is another study of another dwarf galaxy, the Sagittarius. Yeah, the Sagittarius dwarf spheroidal, and it has even bigger. It's 2.5 times the multiplicity of the Milky Way, for example. But yeah, the data set of them is it's too small to maybe to draw a final conclusion on that. Okay.
Got a lot of information.
Yeah, yes.
But.
I'm also a little busy.
Is one of the implications that if the source cloud for star formation has higher metallicity, that changes the probability of certain evolution paths, whether it's going to multiple star system or a single star system, that the metallicity has a significant effect on
Yeah,
the proportion of the
metallicity. Yeah,
stars.
it seems to have as well as the distribution of the abundance as well. But that's another. This is a step forward where we are. Yeah. But that's the final for this. Yeah, next one. No.
I don't know that, sorry.
Oh, yeah. The future work is write the paper. I haven't read the paper, and still I had to really see what is going on with the uncertainty on the ray velocity because the signal is low. So yeah. Okay. And the last part of my talk, robots. This is SDSS-V. This is the phase which is working now. Okay. It is composed by the Milky Way mapper, which is kind of extension of the Apogee. Okay. The black can go back, please.
Oh, excuse me.
This is Galactic Genesis. It aims to cover a bigger chunk of the Milky Way and some other dwarf galaxies in the surrounding us. Next one. The black hole mapper. We will do, for example, an Rosita follow-up. And next one. And this is kind of interesting, or more interesting, or is the local volume mapper, which has an IFU. It's composed by a very small telescope with a big, very big fiber. And it will resolve the intellectual medium in the Magellan Cloud with 10 parsecs. Which they are taking data right now. The data looks really amazing. We are seeing very crazy stuff now in the clouds and also in the Milky Way. Next one. This is the last map they made with the SDSS-IV data. And this is a combination of Planck as well and SDSS data, and it's going back until almost the beginning of the universe. And this is SDSS, part of the legacy of this until SDSS-IV.
So what part of the spectrum is it looking to get redshift 5?
Hmm?
What part of this, how far into the infrared are you looking to get redshift 5?
No. Some of this is combination also with Planck.
Oh, I see.
Yeah, the farthest stuff is Planck. Okay, that one. Okay, but how we are doing this new survey? Okay, I hope this robot will not kill us. But yeah, robots. Instead of having plates and fibers, as before, especially plates, we have this robot, or called the fiber positional units, and they have an apogee fiber, a boss fiber, and a metrology fiber to know where they are. Okay, I have to mention that the boss spectrograph, it was composed by 2 spectrographs actually, and one of them was sent to the south. So now they are observing with apogee and both at the same time. Okay, so
Is the ends of the star big enough to hit all 3 fibers at once?
no,
You
it's
have to shift it for each
yeah.
one.
I will show how they move because they really good. We don't have any more cards. We have the focal plane system where this robot lives, and you can see them here. Light the metrology lighting the robots. That one. Ah, yeah, you have to read. Sorry about that. And it will ask for the next one as well. You have, yeah. So this is a simulation of how the robots are moving. The head of the robot is just there. And it's important to calculate the trajectory without making a collision. So it's very complicated at the beginning, but they do that now. Okay. And this one, you will see now in real time.
I would have never got here.
Okay. So this is that robot actually moving and not colliding. So this is this is the biggest technological advance they achieve with SDSS-V.
And the sky is to the right here. Place
Yeah.
in the sky.
Exactly.
It's a shame that you used to do by hand.
Yeah, yeah.
So these are the
That's less
tiny
than an
little
hour.
tips right there and over there.
Wow.
So who designed it?
Oh, it's just mine.
This is based on in a design from the DESI, the Dark Energy Survey. Yeah.
What's the old story about the railroad track hammer and the robot that comes along?
Yeah.
They have a competition.
But yeah, that's what's going on now. Key takeaways. Okay, SDSS is the daily map of the universe. Apogee to south, hundreds of thousands of high precision spectra of stars study the galaxies as well. Explanation of the distant model of the SMC. Clear estimation of binary reflection of the Magellanic cloud. This is haven't done before. And these robots and the SDSS-V are giving us new insights into the interaction in the LMC and the SMC. You can see here that this is a slice of distances. We didn't have that coverage before. We have this coverage now, and we are seeing the region of the bimodalities very clear. This is the systemic distance of the SMC, and this is the foreground subpopulation, which might be maybe a new galaxy, another galaxy. Yeah, thanks. That's all.
Like this.
Yeah, I suggest you hold that up, but we don't often see
Mm.
basically the eyepiece of a huge telescope.
Yeah.
What that is.
So this is a plate.
Do you see the curvature in it, or is that too?
No, no,
small?
it's too soft. Well, yeah,
The curvature was created by sitting in a ring and then you press down. the
exactly,
bolts,
exactly,
And the bolts push it down. into the
exactly. Yeah,
I don't know if you can see from the back, but if we held it against the back like there, these are all holes in there. You can see right through them.
You can point it towards the camera if you'd like to. Right there.
Oh, yeah.
The camera's right there. Right.
Oh, yeah.
Oh, I was saying on the Zoom camera, the Zoom camera, you can see it.
okay. Well, yeah, I have a, what is the fiber? Who had the fiber? Well, yeah, but you can come see the place you want, take pictures. Yeah.
So when did that robot start, I mean, I guess those plates are now obsolete, but when did the robot start?
Yeah.
So,
Yeah.
When?
When it started in the beginning of 2022. Yeah. Yeah. But I mean, it's not as easy as it looks like. That stage of non-collision of everything took years. And right now they're still adjusting everything because when you equip equipment, everything goes wrong at the beginning. And you have to fix, I think maybe for the SDSS-IV, everything will be working in the way they intended to work.
So I was a little bit confused about what was designed and developed at UVA. Was it
Was
old school thing or the new?
the spectrograph,
What?
the spectrograph.
Okay, okay.
So what
Yeah,
that-
the
what
thing
that
that-
is-
the thing that the 300 thing plugs
Yeah,
into.
exactly. Yeah. And if you have a light, you can see actually the,
How about that? Oh, yeah.
That's the laser pointer.
That's.
Yeah.
Oh, that's you pointed to it.
you see? And it's very tiny.
Yeah,
very
yeah.
small.
Yeah, very cool.
Yeah.
It's a tiny,
Yeah.
tiny.
You succeeded in not making an ass of yourself.
Now that picture is for now,
Or a bird.
full of us now. So,
Any questions? Any other questions?
When will your papers be coming out?
I mean, the first one is already out, and the other one is work in progress, and the other one is work in progress. I need to see it and hopefully soon.
So, a very basic question. It might be related to this, maybe it's not. So they use redshift to measure how far away the galaxy is, right?
Mhm.
And then you also have older stars like Antares, red just because they're getting older. So how do you know which one you're measuring? Distance, speed, or just?
You mean how differentiate it a galaxy or a star? Or?
Well, I'm just trying, if you're trying to measure, like, let's say, for instance, is it a far star away or is it just very old? How do you know if they're both red?
Redshift is something different from being red.
Well, it's a
Right.
spectral line. You look at the line and how it's moving.
The peaks is visibly shifted, actually see.
Mm.
Okay.
Shifted to the red.
Got it.
If it's a red or star, the whole spectrum kind of goes like this, as opposed to the individual bumps, which will be off.
Other lines in the red part, yeah.
Okay. All right, thanks. Any other?
How are the plates made? How, you said there were thousands of them.
Yeah.
How did they make them? Like this, how is it all divided into all these unique?
How did you steer?
Oh yeah.
How did you steer the drill press?
The beginning is to select the targets for a region of 1 degree in the sky. When that passes some quality assurance for that, they go to a CNC, which is not using that, which is the plates are pre-made. They bought I'm blank, and with CNC they did the holes for each design, and it has to be very precise because
Each one is just targeting this very specific.
Yeah.
place.
exactly.
What are the printed lines? The kind of segment that thing, the
Yeah.
sections mean.
Oh yeah, this is a plate for apogee. A place for apogee. And the other one is the position in the sky.
I think.
No, I know that the lines that separate make
Oh.
regions on it. You know, there's
Oh, yes.
like
Yes,
arbitrary regions in the sky. What's the
the fibers are bundled in by 6, 2 red, 2 blue, and 2 black. So each region here has 6 fibers. So you plug by bundle. It's a way to help us to not to make mistakes. There were some places where was actually impossible to plug, especially where bad design. We tried to plug this, and because all the stars were here all together, it was a cluster, but it was impossible to plug. So
yeah, so I can't see it very well, but can you see the red, can you see the color of the fiber thing
Yeah.
from that side?
Yeah, each of these circles, 2 red circles, two blue circles, 2 black.
Yeah.
How do you disambiguate 2 reds and 2 blues?
Yeah, right.
In a bundle?
Are they
Yeah.
Individually marked.
Right, how do you disambiguate?
I don't. It doesn't really care. The only that care is the color.
So if I put in 2 blue ones
doesn't
in
matter
one
which
region, it doesn't
one.
matter which blue goes in
Yeah.
which.
Because you are mapping that after, and you know which.
Oh,
Yeah.
Of experience to back on.
Yeah, I actually I forgot so much stuff about this now, but I'm trying to remember, and maybe a bit sad, because it was really a fun time there, absolutely. Yeah, damn roads.
in retrospect, it's always fun. But when you were there then.
No, I was stressed out and sleep deprived, and
Which dome?
wife was not having back at home because I wasn't there.
Which one of these domes did you use?
No, no.
Oh,
This
none
is
of
this is a view from the DuPont to the rest of the observatory. And here, this is the Polish telescope, the SWAP telescope, and there are the Magellan, the twin Magellan telescope. And here is there the casino and where we live. Yeah. No, it's kind of a small city there. Yeah, it was really fun actually. Especially when the weather was bad, was bummer, but we tried to play games and yeah.
What was the altitude?
2,500 meters above sea level. We did a big party when this finished, and yeah. Good.
All right.
Thanks so much. So we appreciate you being here, and for that, we have the coveted Cass coffee container for your caliente beverages.
Nice.
So thanks so much for coming. This
No,
is fabulous.
Thank you for
Much
inviting me.
appreciated.
Thank you.